Hello, everyone. Welcome back to the AAS YouTube channel. And this is the good stuff, the AAS Author Series. And I'm super happy to have Sarah Leslie with us today. Hi, Sarah.
Hi, and I'm super happy to be here to talk about my paper. So
Awesome.
Thanks for inviting me.
Well, it's a very nice paper, and I'm happy to be chatting about it. Where are you at, Sarah?
So I'm in Leiden at the Leiden Observatory.
Okay.
Yeah.
When did you start there?
Sorry, I've been here for about a year now.
Oh, okay.
Yeah. So I did my PhD in Heidelberg in Germany at the Max Planck Institute for Astronomy. Mm-hmm. And that's where most of this work that I'm going to talk about took place. But yeah, I'm now an Ort Fellow in Leiden.
Congratulations.
Thanks.
Looks like you are actually maybe in your office there at Leiden.
Mm-hmm.
Are you guys back from the pandemic, or what's the scene there?
So we're allowed to come in a couple of days per week. We have a booking system so that they make sure only one person is in each office, or however many people can fit within the social distancing rules. Semester starts next week, so I'm not sure how busy it's going to be. Right now, over the summer vacation, it's been very quiet. But I also really enjoy working from home as well. So
yes. So we started last Tuesday, so we've been going for about a week into the semester. I'm totally online, so it's not that big of a deal, but we shall see how things go over the next week as far as testing. And there's certainly been a number of places in the US that have opened and then 1 week later been forced to close because they've had a spike. So we shall see where we go. But yeah. So Sarah, what do you like to do for research?
So I am an observational galaxy evolution person, and I really like using multi-wavelength observations to put together pictures of galaxies. And I've worked both in nearby galaxies and high redshift. So all the redshifts, all the wavelengths, I guess.
Cool. And that will bring us to this really lovely paper on the VLA-COSMOS 3 gigahertz large project, evolution of specific star formation rates out to Z of order 5. And Sarah, take us away.
Great. So this work was a major part of my PhD thesis. And during my PhD, I was working with the VLA-COSMOS 3 gigahertz large project, where Vanessa Smolcic is the PI. And this was, so they conducted 3 gigahertz observations with the VLA of the entire cosmos field. So it's a 2 square degree field. And at the time, this was the deepest radio continuum survey over such a wide area. So it's 2.3 microjanskis per beam. And it's also at quite a high angular resolution. So 0.75 arc seconds resolution. So the cosmos field is one of these extragalactic Hubble fields. And it has observations in lots of wavelengths. So we have over 30 bands of photometry, which I'll get into in a little bit. But maybe for some introduction on measuring star formation rates and cosmic evolution of galaxies. So I guess we know that the cosmic star formation rate activity of the universe was peaked at around redshift 2 or so, and then has been declining ever since. And at higher redshifts, this was also smaller because it took some time for galaxies to start really, fueling up. So this is the classic Maddow-Lilly plot. Yep. But at higher redshifts, it's hard to get a census of the dust-obscured star formation that's happening behind, because like infrared observations, which would be great for probing this dust process emission, is often so from Herschel, for example, it has a fairly large beam, so it's quite hard to deblend the sources. They're blended together to work out what emissions coming from what galaxy and so forth. So another potential way forwards is to use radio continuum, because we have these interferometers like the VLA, so we can get higher angular resolution. And also because it's at this long wavelength, we're not affected by dust attenuation. And so the radio continuum traces star formation at a few gigahertz. It's composed of like synchrotron radiation and free. And the synchrotron comes from supernova remnants, so it's kind of related to the death of stars. And the free comes from like warm H2 regions, so it's related to the current star formation. And yeah, so I will talk a little bit about the star formation rate calibrations in a bit, but maybe let's go to, I guess, the first figure, but that's just a schematic of the COSMOS field.
Go ahead and blow that up a little bit, and boom, boom.
So it's showing the different areas where we have different photometric measurements. In the background is the noise map of the VLA data that I was using. So it's a mosaic of 192 pointings with, I think, over 100 hours.
And
so
the white optical.
Sorry, and the white is masked out regions, and there's 4 deep ultravista stripes where there's extra deep data. So
okay.
Yeah, and the red box is the region that I'm using for my experiment. So I guess I should say the aim of my work was to measure the star formation rates from the radio continuum and to look at the star formation rate stellar mass relation, which we often call the main sequence of galaxies. And so even though we have this really deep radio data, if we just look at the detected sources, so say at about above 5 sigma, we're only looking at the most massive galaxies. And I wanted to look at down to more fainter, low mass galaxies. So to do that, I use a stacking technique. So I just take because we have the deep optical and near-infrared data, from which we have the stellar masses and photometric redshifts from the COSMOS collaboration. So I take the known position of the galaxy and take a cutout of the radio image, and I combine them, the cutouts using a mean, and then we can get an average flux for the population. And I think the next figure, which is figure 2, shows how I'm binning the galaxies in bins of stellar mass and redshift.
Ooh, nice.
And so I also talk a little bit about how we separate star-forming galaxies from passive galaxies. So we use a NUV minus R minus J color cut.
Okay.
I also remove AGNs selected via various multi-wavelength tools, or if they're super bright in the radio, they might be a radio AGN. So I remove them from the sample before calculating the stack. And this kind of, the grayed out, gray shaded area is where we're not mass complete in the COSMOS field. So above that, we think we've got a representative sample of galaxies. And the numbers show how many galaxies there are and also the color. So there's always at least, say, 60 galaxies in my stack, but more often it's hundreds or thousands of galaxies that I'm combining together.
So let me ask a question then. On the last rows where you're in the mass bin range of about 8.5 to 9, it looks like, I mean, the raw numbers, if those are the raw counts, seems like that's a lot of galaxies, but then there's 0% under each one. What is the 0?
So 0% detected. That's what in the 5 sigma catalog.
Got it. Okay, good.
Yeah. So if we were just looking at the radio detected sources, yeah, we don't have any at these low masses.
Got it.
The radio is really faint for low mass galaxies, which is interesting. So let's go down a bit more.
Sure.
I think the next figure is talking a bit more about the radio star formation rate calibration. So I measure the total fluxes from this stacked image. There's some examples in the appendix. And then I convert this to a luminosity using the redshift. But then to go from radioluminosity to star formation rate, there's a lot of different calibrations we could use. And so this was just showing different calibrations from the literature and how that can introduce some systematic differences in your star formation rates.
Okay.
Yeah, so. So I'm using a calibration that relies on the fact that there's a tight correlation between infrared luminosity and radioluminosities of galaxies from the local universe.
Okay.
And extrapolate and using the same calibration at all redshifts. But this is.
Okay. I'm with you.
All right. So then I think the next figure is one of the first main result, I guess. So here shows the star formation rate stellar mass relation. On the left is for these star forming galaxies, which were the bluer colors, and the red is for all galaxies. Based on some simulations that we did, we found that if the stack flux doesn't have a signal to noise greater than 10, we don't really believe it. It's likely overestimated. So that's why some of the sources are triangles. So yeah, in this figure, you can see that
triangles here,
yeah. So the color is redshift, and there's a relation between star formation rate and stellar mass. And I claim that it isn't just a linear relation, that it has a statistically significant evidence for some curvature, some flattening at the high mass. So that's one thing that different studies find different things. And we talk a little bit about that in the discussion, why that's the case. So yeah, and then this is something that has been done before, but it's nice to do it again with the radio using just one consistent data set and one consistent calibration across the whole field. And as I mentioned before, the radio is not affected by dust attenuation. So that's nice. And I provide this functional form, which is the solid lines. So if you just want to use this to plug in a redshift or a stellar mass. And,
that would be this dark line here?
So that's the relation extrapolated down to redshift 0. So I should say like my lowest redshift is 0.3 because the cosmos field isn't, although it's a large area, it's only 2 square degrees. So for local galaxies, you're not getting a good representative sample.
And so that scales then up to higher Z. Okay.
Because I thought it'd be nice to have just a continuous function for people.
Yeah, people like that.
People like that. All right. But all the individual measurements are provided in tables at the end. So if you wanted to look at that.
Very nice.
All right. Let's see what the next figure is.
There's our best fit parameters. We want to stick it in. Characteristic mass. There we go. And
so I think the next figure is just showing the best fit parameters from fitting those data with the function. Yep. And figure 6 is just showing the same data in a different way. So instead of star formation rate, it's a function of stellar mass. It's specific star formation rate. Redshift.
Here. Yep.
And in the background, there's some literature comparisons.
Let me ask a general question then. What sets the size of the uncertainty bars in both directions?
Good question. So it's when I calculate the mean, I also do a bootstrapping analysis, and so with replacement and And so I calculate, I think it's the 16th to 84th percentile of the and I redo the stacks. I don't remember how many times, I think 100 times, and then give those. So it's a variance from, it's a measurement of both the variance within the bin that I'm stacking,
right,
as well as a little bit of the uncertainty and fluxes.
So that would seem to describe and maybe I'm being naive here, maybe I could see how that would be the uncertainty in the, if you like, the Y direction and the log S. How about
sorry. And in the X direction, it's it's basically from the binning, the size of the bin, but it's the 16th to 84th percentile of the redshifts in each bin. Yeah.
Okay, thank you.
Okay. So next figure, I guess this is a bit involved. So what I did next was I took stellar mass functions from Davidson et al. 2017, which tell you how many galaxies there are at a specific stellar mass. And these are also derived using the same data in the COSMOS field for star-forming galaxies, particularly.
Okay.
And so then I multiply the main sequence that I derived by the stellar mass function to get the total star formation rate density as a function of stellar mass here. So in the top left panel is showing all the redshift bins together. And the vertical lines are showing the mass completeness limits. So at low redshift, we're complete down to fairly low masses, just below 10 to the 8.5, whereas when you get to high redshift, it's more like 10 to the 10 point something. So we don't trust those results there. And then on the lower two panels, it's the same figure, just broken up into low redshift and high redshift, and showing the error bars, which is, if I recall, it was mostly the evolution within the bin, combined with the uncertainties a little bit.
Okay.
So I also drew a little, I think it's a square that shows where the peak of this cosmic star formation rate density is. So, so these ones, but also, so those data points here correspond to the mass at which this curve is peaking.
Peak.
Yeah. So it's a peaks distribution. So it's saying at a particular at a given redshift, there's a characteristic stellar mass of a galaxy that's contributing the most to the cosmic star formation rate density. And then on the top right figure, it's showing this peak mass and how that compares to the turnover mass. So that was the mass at which the star formation main sequence, the star formation rate stellar mass relation, was starting to bend over. And so that's the reason why there's a peak and why there's this evolution. Because we're finding when you're at high redshifts, actually there's very little bend in the main sequence. But as you go to lower redshift, you get more and more of a bend in the main sequence, and that bend is occurring at lower masses.
It's broadly consistent with others, Gavazi, for example, or
so some of these things are a little different. I think the Gavazi result is I'd have to read the caption again, but so this evolving characteristic mass is seen in a lot of other relations, such as the stellar mass halo mass relation. Some people find that the where that peaks is also going up with redshift, or the size mass relation also has a little bend, and it seems like all these things are kind of evolving similarly.
Okay.
But yeah. Okay, and so then we can investigate this a little bit more in the discussion, but
we can if you like.
Yep. But I guess the next figure is if you then integrate this star formation rate density as a function of stellar mass over the stellar masses, then you can get the total cosmic star formation rate density. So this is the Lilly Maddow Dickinson. So this is the black line shows the literature consensus result from Maddow and Dickinson. And the blue symbols are from my work. And you can see that they're a little bit high at low redshifts.
Right.
But there's a lot of assumptions that went into getting these numbers. And in the background, I'm comparing to other infrared and radio measurements. So I kind of investigated some of the systematics that go into this. So one thing that I talked about at the beginning was the different star formation rate calibrations that you could use. So on the right, I'm showing the result if you so instead of extrapolating beyond where I've measured the fluxes, just taking those flux measurements and converting that to a star formation rate. So I'm not correcting for any incompleteness here, but just the point is to demonstrate that there's quite a large variation that you get just from using the different star formation rate calibrations. And the purple little arrows are from Leiden Novak et al. 2017's work, where we were using the direct detections and making a luminosity function. But so this just shows the limits from the direct detections.
Okay.
Yeah. So there's a lot of extrapolation involved always when going from a luminosity function to a main sequence to a cosmic star formation rate density, and a lot of assumptions as well. So I guess what I learned from here is maybe we don't know the cosmic star formation rate density as well as we think we do.
Yeah.
But, yeah. Okay.
Got a few steps in them.
Yeah. All right.
Where shall we go next?
Shall we? Let's just keep scrolling.
Keep scrolling.
I think next I looked at different galaxy morphologies. So it's been well shown in previous works that spiral galaxies have higher star formation rates than early type galaxies, and galaxies with a bulge have a lower star formation rate at a given stellar mass. But it's nice to do this again in the radio. So I split the sample up based on 4 different morphologies, which have been determined from using the Hubble I-band images.
Okay.
And I broke them into 4 classes. So the one on the left in the top row is like the early type spheroidal kind of galaxies. And for here, it's kind of hard to measure a star formation rate for a lot of them. That's why they're in a transparent color, because the signal to noise was did not meet my criteria to be included in analysis. And then we have the galaxies that are late type, but they have a significant bulge, and then the disks, and then the irregulars. So what I see is that the irregulars have the highest star formation, at all stellar masses, and then the disks, and then the bulge dominated galaxies, which is what we would expect. And I also found, which you can't really see just from this figure, but if you just have one morphological type class in your sample, we don't see this bending of the main sequence that we saw with the full sample, which is what I've drawn in the background, that bending relation.
Oh, yes.
You only get the bending relation when you include the full mix of morphologies. And because we found that the mass at which the bending bends over, the bending starts to occur, was decreasing with decreasing redshift. Maybe that says something about how bulge dominated galaxies are more prominent at lower redshift, there are more galaxies with bulges and a suppressed star formation.
IRR. Okay. I'm with you. I'm with you.
Okay. And the bottom panel shows the same thing, just in a different way in different redshift bins. Yeah. So the data is a bit noisy, but let's I guess move on to the next figure. Which
question? Which of the morphological types here? I mean, there's various ways you can answer that, but which type sort of dominate the sample?
Yeah, I guess that depends on whether you mean dominates in terms of numbers or dominates in terms of star formation.
Let's go by numbers. Let's go by numbers.
Yeah, and that kind of actually brings us to the next figure.
Okay.
Which is showing the fraction of star formation coming from each type.
Thank you. Okay, this is by number?
No, well, this is by star formation.
Okay.
So what I did was I took the average star formation and then multiplied it by how many galaxies there were in that type.
Okay. Weighted by number.
Yeah. So although the disk at a particular stellar mass and redshift, the disk or the irregular galaxies have the highest star formation, there's not so many of them compared to, for example, at low redshifts where you have a lot of bulge dominated galaxies at high mass. So that's the brown kind of color. It's kind of interesting to see that the disk dominated galaxies always have this peak at around 10 to the 10-ish.
Yeah. Cool. Okay.
Yeah. Right. But for the numbers, I think you can see in the appendix maybe. Yeah. So I also tried looking at environment, if we're ready to. Yeah. So I looked at two different ways of probing galaxy environment. One is the number density. So how many galaxies are there in a given co-moving megaparsec cube squared. It's surface density. And I used catalog from Scoville et al. 2013. Okay. And then I normalize at each redshift, normalize by the average for that redshift, because the average density of galaxies is changing with time. So the numbers are something like how many galaxies per megaparsec squared. Yes. And anyway, so from there's the low density kind of corresponds to void-like environments, whereas the average density is field. High density is like groups or filaments, and high density is clusters. But and so here in this figure, I'm just showing the star-forming galaxies, the blue ones. And I didn't find any statistically significant difference in the main sequence derived in the different environments. Okay. So that's something that's different people find different things, different studies. Although when you're just looking at star-forming galaxies, I mean, the effect of environment seems to be rather small, like a something like 0.5 or less dex, and it seems to come into play at lower redshift samples. So this could say something about the quenching of the environmental quenching effects only either happen very quickly, and so these galaxies drop out of the star forming sample, or that it's a weak effect at high redshift. Whereas before we found that morphology was a very strong, there was a very strong correlation with the star formation, the main sequence and the morphology.
Interesting.
Yeah. So there is of course the fact that there are more quiescent, there's a higher fraction of quiescent galaxies in denser environments. So there is some kind of, and some people say that this is, this is in addition to the morphology density relation. So I think this would be one area where larger statistics, larger samples would be helpful, because they don't have enough galaxies even within the cosmos field. Yeah, and the other way I looked at environment was looking at X-ray groups. So galaxies that live in X-ray groups versus galaxies that don't live in X-ray groups.
Okay.
But I didn't find any results there, any difference. But I only have here one measurement with a signal to noise greater than 10. So, yeah. So the other fun thing about this paper is I compare my main sequence with a lot of other results from the literature. So that's figure 14 on the right. I'm showing at one particular redshift, redshift 1. So you can see that so on the y-axis, it's the star formation rate from my main sequence minus the star formation rate from the other literature main sequence, taking into account IMF. They might have used a different IMF. And you can see that my star formation rates tend to be a bit higher. And I think this is due to, in large part, the star formation rate calibration. Recent studies, for example, Katsianis et al. Found that infrared star formation rates can be overestimated often, and my star formation rate calibration is really relying on the infrared star formation rate, the infrared radio correlation. So that could be one reason, but there are others potential. But yeah, it's okay.
A bit of spread.
There is a bit of spread, yeah. Oh, and I should have mentioned earlier that this work is a follow-on from Karim et al. 2011. So Alex Karim in 2011 did a similar study, a stacking analysis in the cosmos field using 1.4 gigahertz radio data that they'd taken. Whereas now we have 3 gigahertz data, which is deeper and a higher resolution. And since then, there's also been deeper multi-wavelength photometry. So we have better stellar masses and redshifts. And also we can start looking at things like morphology and environment with the radio. Yeah, so those are, I guess, the main results. Okay. Here I was trying to see if you could, if for the bulge dominated galaxies, so the galaxies that have a disk and a bulge, whether the disk component was formed following the star formation rate stellar mass relation of the pure disk galaxies, or whether maybe they had a suppressed star formation because of the presence of the bulge. But unfortunately, I couldn't really say anything because the systematic errors are about 0.2 dex, and that's about the size of the effect that you would expect morphological suppression to have. And also, I didn't have good bulge disk decompositions, so I was just using the bulge to total stellar mass relation from Lang et al. 2014. So.
Okay.
Yeah.
Conclusions.
Yeah.
So, okay, to sum up the work, what would you say?
So I guess we've used the radio continuum to derive a fairly uniform and consistent star formation rate stellar mass relation out to higher redshifts than done before with radio. And we see that there is a characteristic stellar mass that was contributing the most to the star formation activity in the universe. But this characteristic mass was increasing with redshift. And that's consistent with the idea that the massive galaxies formed first and then quenched first. So it's like this downsizing picture. And that we found that the growth of bulges has an important role to play in the decrease of star formation towards the present day.
Okay. There's a whole lot of appendices. You want to go through them, or would you like to?
Sure. I'll just show some of the figures from the appendices. So in the appendices, I'm discussing a lot of details about the stacking, which drove me crazy because there are a lot of choices you can make. So do I do a mean stacking? Do I do a median? How do I measure the total flux? Do I do an aperture? Do I fit a Gaussian?
Right.
And then that's also with all the other decisions that you have to make, like which star formation rate calibration do I use? And all these, are these results consistent with the direct detections? So yeah, a lot of the times I felt like I was going around in circles while writing this paper and replying to the referee, who did a great, I really applaud them because they thoroughly read the paper, which is a big effort. I get tired even now talking about this paper because it's so long.
No, I understand. Well,
Yeah.
By the time you get to this point in the paper, you're, at least me, I'm so tired of seeing it that I don't want to see it anymore.
Yeah.
But I get it.
And so we did some simulate. Maybe we could go to just quickly to figure A3.
A3. A2 and A3. Okay, so there's some examples. Stacks.
Yeah, these are just some of the examples of what the stacks look like. So I was stacking in the image plane. And it's quite difficult because you have because with radio data you have to clean the image down to some threshold, and then I'm combining cutouts that have been cleaned. Like some sources have been, I still have the bits of the dirty beam in there, and yeah, it's a bit messy. So, but yeah, so the simulations also that we did, where we were just inserting fake sources into into maps with a Gaussian noise. So that's also not, there are limitations that to the simulations, but I think we made a signal to noise cut I mentioned of 10. So the two example stacks on the left wouldn't have been included in the analysis, even though they have thousands of sources. So the number of objects is over 3,000, but the peak signal to noise is only about 5.
Okay.
And this is at the low stellar mass end. So that's interesting, I guess.
Yep. So it kind of points to future directions a little bit.
A little bit, yeah.
So if you could, where do you think the field should go, or what do you think we're doing over the next couple of years that would help improve the situation or improve some of the agreements between the different calibrations and so on? So.
Yeah, so I'll just focus on the radio in particular. I mean, I think we need to do quite some more work on the radio star formation rate calibration. Because how
would one do that? How does one do that? How would one improve the calibrations?
Well, I would like to better understand the how it comes about. So we have the infrared radio correlation, and the idea is that comes because they're both related to massive star formation, but there are a lot of different models for how this should evolve with redshift, and the observations that we see are not going in the same direction as those models.
Right.
So that's one thing to look into. And there's a lot of conspiracies as to why this correlation stays so tight. Because when you go to low mass galaxies, they don't have as much dust and metals. And so the infrared should be less, but then also the radio synchrotron may escape more or something. So there's like a conspiracy as to why this relation is so tight. And maybe that's not actually related to star formation rates. So comparing it with other star formation rate traces would be helpful. And also just understanding the infrared radio correlation would be helpful. So that's one thing that I'm going to be working on, and especially at higher redshift. So one of the groups that I'm working with here in Leiden has a deeper observation of the cosmos field. So we can do this with more detections instead of stacking, and we can also look at the infrared radio correlation to look at fainter sources. And then also what would help with these kind of studies is going wider as well as deeper. And for that, I'm working with LOFAR.
Oh, okay.
Yeah. So this is a low frequency radio telescope that the base is here in the Netherlands. But it's very impressive actually. So it's a lot, because it's at 150 megahertz, the radio emission is quite a lot brighter there than at a few gigahertz. So you can get to equivalent flux at 1.4 gigahertz in less time.
Right.
And there's a very large field of view because it's at these low frequencies. So yeah, there's the LOFAR deep fields, which cover a much larger area than Cosmos. So I'm interested to see what's going to come out of that as well. And this is all in preparation for the square kilometer array and these things. So I think if we want to really use that to understand the universe, we need to understand what we're looking at, I guess. Yeah.
Very cool. Very cool. So the future's bright. Lots of things to do. Very cool. Very cool. Well, Sarah, I want to thank you so much for spending some time and walking us through your really lovely paper today.
Yeah, thanks for all your attention.
Very much. And thank you, everyone. And we will see you on the next one. Bye-bye.
Bye.